Again, it's a rich thing.
What is going on, guys? Welcome back. In today's video, we're going to implement linear regression from scratch in Python. And a warning right ahead, it's gonna be mathematical. So let us get right into it. All right, so let's get started with the very basics of linear regression. What is linear regression and what can it be useful for? And we're going to start with an example right away. Let's say we have a bunch of students and these students have an exam and they have a certain study time. Each of them has a certain study time that they invested for this exam. So let's say we have the study time here. It can go from 0 hours up until not really infinity, but pretty much infinity depending on what the maximum number is of the students. So you can study 2 weeks in advance, 1 year in advance. You can study 1 minute in advance from 0 up until, let's say, limitless. And then we have an exam score. And the exam score is the actual result of the test. And it can go from 0 points to 100 points or from 0% to 100%. So what we can do now is, let's say we have a data set with these data points and we want to plot this here on a two-dimensional coordinate system. Now, it's not the most beautiful coordinate system, I know, but let's say the x-axis is the study time and the y-axis is the exam score. Now, if we were to visualize all these points, we would probably see something like that with a bunch of data points here. People who don't study at all and get pretty low scores. People who study a little bit get better scores, but still some that get pretty bad scores and all that. And we can see all these data points, people that study a lot and get a lot of points or a very high score. Then some people who study a lot and don't get very good grades at all. Some people who don't study at all and get very good grades, those are the outliers. But most of the points are going to be somewhere here in the middle. Now what linear regression tries to do is it tries to find a line that fits these points the best. Now best is a little bit subjective because certain regression types or certain algorithms use different approaches, because some say, okay, I don't care about outliers, I care a lot about outliers and so on. Depending on what you want, you have to choose a different procedure. But for linear regression, what we're interested in is minimizing the error. And the error is basically, let's say I have a linear function here, a blue line like that. And this is obviously not the best function that we can find for these data points. But the error of that function would be to basically go for each point and see if this function was correct. We would predict that for this x value here, this would be the y value. And then what we do is we just go down and see, okay, this here is the error, and this here is the error, and this here is the error. This is just the difference from the prediction to the actual reality. That is the error, okay? And what we want to do is we want to find a function that minimizes that error. And this is what linear regression is about. So the structure of a function is basically, of a linear function is basically y equals m times x plus b. So m is basically the steepness and b is the distance here. So we expect the final line to be something like that, to be pretty much fitting the points, maybe be influenced a little bit by the outliers and so on. But all in all, we want them to fit most points. We want to minimize the error in total. And for this, of course, what we need to do is we need to minimize the error function. The actual minimization process is a little bit more complicated, but the error function in and of itself needs to be defined first so that we can minimize it. Because in order to minimize something with the gradient descent algorithm that we're going to talk about in a second, but in order to minimize something, it has to be something that produces a value, because we want to minimize the output by tweaking the little things that we can't tweak. In our case, if we look at m times x plus b, we want to tweak m and b so that for x, I get the best possible y with the least error. And the error function needs to be defined in order to minimize it. So the error function is going to be capital E, is going to be 1 divided by n, which is, I'm going to tell you in a minute, because in a second, why it's 1 divided by n times the sum from I equals 0 up until n. And now we get yi, which is the actual value that we get here. So this point is yi, and this point is yi. The y value of this point is the actual yi value. And from this, we subtract yi hat, for example. So this is just the predicted value. This is this value here. And we can actually remove that and replace it by m times x plus b. So that is the error, and we can square that, and that would be the mean squared error. And we can add an I here to make it a little bit more accurate. So if you have never seen this before, this is called the mean squared error function. Don't be confused. It's not really complicated. It may look complicated because it's math, and for a lot of people, math looks just complicated. But all we're doing here is, this is a mathematical way of writing that for each point, and n is the amount of points, for each point from the 0th point, from the first point to the last point, what we do is we get the y value of the actual point, so this y value here, or this y value here, or this y value here, the actual value, and we subtract the position of the function y value. So if we have a function like this, we will take the actual y value here and this y value here, and this is the difference, so this is what we're going to get, and then we square that difference. And in the end, we take all these distances, all these errors that we have, and we divide them by n, which is the amount of points, so we get the mean squared error. The mean squared error. So this is what this function does. It's just a fancy way of saying, take the difference from all the actual points and what the function would predict the proper y value would be, square that difference, and divide it by the amount of points that we have to get the mean squared error. This is the error function that we're trying to minimize when it comes to linear regression. Alright, so this next part here is going to be very technical and mathematical because we're going to talk about partial derivatives, about calculus. So if you're not interested in that, or if you don't understand calculus at all, you can skip to the coding part directly. I would not recommend it because even if you don't understand everything, it's good to just understand or listen to what is happening behind the scenes, even if you don't understand all of the math. So I would recommend you to watch that part as well, but it may be a little bit boring because it's very technical and mathematical. I personally think it's one of the most exciting things to understand what is exactly happening, how does this optimization work, but I can understand if some of you guys say, I don't want to listen to that, I want to get to the coding. Just keep in mind that you won't understand fully what is happening behind the scenes. So let's get into it. We want to minimize that error function. We want to get the lowest possible e for our line. We want to find the line that gives us the lowest possible e. So the only thing that we can influence is the m and the b. The x is just the input and the y is just the output. We want to find m and b so that we can minimize e. That is our goal. And how can we do that? We can do that by taking the partial derivative with respect to m and with respect to b, because that gives us the direction of the steepest ascent with respect to m and b. So how can we change m to maximally increase e, and how can we change b to maximally increase e? Now you might say, okay, didn't we want to decrease e? Yes, we did want to decrease e, but if you just take the opposite direction, if you have the direction of the steepest ascent, you can just go the opposite direction and you have the direction of the steepest descent. So this is what we're going to do. We're going to take the partial derivative with respect to m and b, and then we're just going to go to the opposite direction of this gradient. So we're going to say the partial derivative of e with respect to m is going to be, or is actually, 1 divided by n times I equals 0 to n, and now we have this squared here, so we say 2 times, those are just the basic calculus rules, so if you don't know calculus, don't be confused, you don't need to understand everything, minus m times xi plus b, and now we need to also multiply with the inside derivative, which is basically just, this is a sum, so we just ignore it, and this is the factor, so what we end up with is negative xi. And now we can simplify that by just extracting the 2 and the negative. So we can say, okay, this is nothing but just minus 2 divided by n times the sum from I equals 0 up until n. And then we have xi times yi minus m times xi plus b. So that is the partial derivative with respect to m. Now let's do the same thing for b. It's basically the same, but the difference is that we don't have the xi because here we don't have a factor. So this is actually the same thing. We basically have negative 2 divided by n times sum from I to n, and then just yi minus m times xi plus b. That is it. And those two things give us the direction of the steepest ascent with respect to m and b. And all we need to do now is we need to go to the opposite direction. That's all we need to do. So if we want to improve m and b, all we need to do is with each iteration we say, take the current m, and what you do is you assign to it the current, or take the new m, what you do is you assign to it the current m minus a learning rate, we're going to talk about that in a second, times the direction of the steepest ascent. So basically E and M, and the same for B. B equals B minus L. This is more of a programming notation, not necessarily a mathematical notation, but that is what we do. So we know, okay, in this direction, let's say we increase the error the most. So what we do is we just go the opposite direction, and we do that with each iteration because it changes, right? So sometimes in this direction, it's going to be the steepest ascent, then in another direction, then again in another direction, especially if we don't just deal with two variables, but with many different variables. We don't do this only with score and with study time. Sometimes we have like 10, 20, 1,000 different features that we have to take into account when doing a linear regression. So it's not always just two things. And this is the direction of the steepest ascent, which is why we subtract, because we don't want to go to that direction. We want to go to the opposite of that direction. Otherwise, we would have a plus here and not a minus. And the learning rate is basically how big, how large are the steps that we take. Now, the larger the steps, the faster we're going to get to the actual optimization. But the lower the learning rate, the better it's going to be in the end. The better the result is going to be because we're paying attention to details much more. So I think we're going to go with a learning rate of about 0.001, which is, or maybe one more zero. We're going to do that. And now that we have all the math handled, we're going to do this in Python. Now we're going to take all this theory and turn it into Python code. And for this, we're going to start by installing two libraries. However, since we're implementing linear regression from scratch, those two libraries are not going to be related to the linear regression algorithm. We're just going to use pandas to load a data set from a CSV file, and we're going to use matplotlib for visualization. The whole linear regression process will be implemented by us from scratch. But if you don't have pandas and matplotlib, you want to go to cmd and say pip install pandas and pip install matplotlib, like that. And once you have that, you can just go ahead and say import pandas as pd and import matplotlib.pyplot as plt. Now what you're going to need is some sort of data set. You can craft your own, you can just make up some values, or you can, if you're comfortable with that, take an actual data set and apply linear regression onto it. For this video, I have just crafted my own sample CSV file, just some random values that have a certain trend inside of them. We have X, Y, and then just a bunch of random values here, randomly generated. However, you can, as I said, go with a real data set, and we can also interpret those as study time and score if you want to. However, I think we have some values above 100, as you can see here, 117. So it's not entirely accurate, but we can just go ahead and call this study time and score. So this is just a basic comma separated value file, CSV file with some random values. We can load them in by saying data equals pd.readCSV data.csv, and then we can take a look at it by saying print data to see the structure of the data frame. Nothing too fancy. 2 columns, study time, score, and the values. We can also go ahead and visualize them by saying plt scatter data dot study time and data dot score, and then plt dot show, like that. And there you go. So those are the data points that we're going to use for this regression example here. You can actually pick any data points. The data is not the focus here. We just want to have a properly working algorithm. So I'm going to delete the visualization here, and we're going to start with the loss function. So we're going to say def loss function. You can also call this mean squared error. And to this function, we need to pass the m value, the b value, and the points that we have, the actual data points. So in our case, data. And what we're going to do here is we're basically going to say we have a total error, which starts at 0. And what we do is we add all the individual squared errors to that. And in the end, we divide by the amount of points. So we say for I in range length and what was it? Points. We're going to say the x value that we have is the points.ilog. So at the location I, we want to have the study time as the x value, and then at the location I, we want to have the score as the y value, and the error is basically just what we had already. So if we look at my paint here, what was the error function? There you go here. This is the error function. We're just gonna write it in a Pythonic way now. So total error, let me just see how I wrote it. Total error plus equals, and then the loop is basically the sum, and what we write in here is the iteration of this sum sigma symbol. So we say to the total error, we want to add y, the actual y point, minus what we thought the y point should be based on m and b. So m times x plus b, and the whole thing squared because it's the mean squared error. And in the end, what we do is we just say total error divided by float length of points, like that. So that is the basic loss function. It tells us how much we're off from the actual result. Now, what you need to know about this loss function here is that we're actually not going to use it, because what we're actually interested in is just minimizing it, and it's already included in the gradient descent, because we cannot just have this function and tell Python take the derivative of it. So we need to do it manually, and we have done it manually already. So this function is more like a function that you can use if you want to calculate the loss manually, but we're actually not going to use it in the final optimization process. So let's go ahead and implement the gradient descent. We're going to call this function gradient descent. We're going to pass here m now, b now, the current values here. We're going to pass the points, and we want to pass a learning rate, L. And what we're going to do now is we're basically going to just start with a gradient for m of 0 and for b as well. And then we're going to say n is just the length of the points, the amount of points. And what we're going to do now is we're going to just perform the gradient descent. Again, we're not going to use that function. This is just a separate function that you can use manually. Here we're going to already use the formulas that we had here. So those two formulas here that we already talked about, these partial derivatives, and those already include the loss function to some degree. So what we're going to do now is we're going to say for I in range n. So for each point, what we're going to do is we're going to take that point. So x equals then points ilog I dot study time, and then y equals ilog I dot score. And what we do now is we calculate the gradient based on the function here. Again, all I'm doing here is just typing these two functions, these two lines, this -2 divided by n, whatever. The loop is the sum symbol here. All I'm doing here is just putting this into Python code. If you want to understand what's happening here, you need to go back to the mathematical explanation. So we're just going to say m gradient plus equals, and then -2 divided by n. Actually, the negative is out here. -2 divided by n times x times y minus m at this particular moment in time times x plus b at this moment in time. And then b is basically the same, but without the x. There you go. Then once we have that, once these iterations are done, we know which direction we have to move into, or away from actually. So what we do is we basically say, okay, the new m is going to be the m now, and we're going to say minus m gradient, so in the opposite direction, but with a learning rate of L. That determines how much we move. Same for B. And that is actually it. And in the end, of course, we return M and B, both values. That is the gradient descent function. We can actually get rid of that function if you're not interested in it. But that is all we need to do in order to perform the linear regression. So now we just need to execute everything. We say, okay, what is M? We start with 0. B, we start with 0. We can pick any starting values if we want to. We will use a learning rate of 0.0001. And we're going to use 100 iterations, also called epochs. We can also go with 1,000 actually. So let's go with 1,000. And now what we do is we just say for I in range epochs. So for the amount of iterations here, we're just going to say M and B are going to be gradient descent of M, B, and the data and the learning rate. So we're constantly going to get better and better at estimating the perfect M and B. And in the end, we can print, not PLT, we can print M and B, and we can plot the results. So we can say plt.scatter data.studytime, data.score, color is going to be black, and then plt.plot, and we can plot the trend line here, which is basically just a list, and we can look at the CSV file. All the values should be, all the x values at least should be more than 20 and less than 80, so we can just go with list range 20 to 80 just to have some values. And then we're going to say m times x plus b for x in range 20 to 80. There you go. And the color of the regression line will be red. And then plt.show. That's it. We can now run this. Maybe you want to print the epoch. So let's say if I modulo 50 equals 0, print epoch I, like that. Inside of the string, maybe. There you go. Let's see if that works, or if we made mistakes. Epoch 0, 50, 100. Let's just turn the number down so we get the results faster. Let's go with 300. And then we should see pretty decent results. 0, 50, 100. And we should see a pretty solid trend line here, or regression line. There you go. Seems about right. As you can see, this is a pretty good, actually, I think it's the optimal linear regression line here, because we had like 300 iterations. Those are the values here for M and B. So this is how you implement linear regression from scratch in Python. So that's it for today's video. Hope you enjoyed and hope you learned something. If so, let me know by hitting a like button and leaving a comment in the comment section down below. And of course, don't forget to subscribe to this channel and hit the notification bell to not miss a single future video for free. Other than that, thank you very much for watching. See you in the next video, and bye.